So, good morning. Hello, sirs. We are the Group 5 and we are here to discuss about the calculation of sextant altitude by stars and planets and example problem for each celestial bodies. So, we are the Group 5 and I'm Lord Sidron Montifalcon and my other members are Ralph Lawrence Montebon and Adrian Gabriel Lim. And our learning objectives for this topic is after the discussion, the student must be able to first know some terminologies in regards to this topic and know how to convert the sextant altitude to true altitude of stars and planets. So here are some terminologies so that as we go further to this topic, we understand what the word means. So what is sextant altitude? The altitude of a celestial body is as measured by a sextant. It is the angle measured in a vertical plane between the horizon and a celestial body without any application of corrections. Then the height of eye is the distance that your eyes are off the surface of the water or the ground. Then the index error. A correctable error in reading of the sextant resulted with the horizon and index mirror are not parallel with the sextant is at 0 degrees. Then the observed altitude is the geocentric altitude of the body, the altitude with respect to the celestial horizon and the center of the earth. Then the dip or angle of dip is the angle of the visual horizon dipping below the true horizon due to your eyes height above it. This is also tabulated in the nautical almanac. Corrected dip is always negative. Then the apparent altitude. The altitude that the celestial body would be at if there were no atmosphere. It is calculated based on the celestial body's coordinates and is always lower than the observed latitude. Altitude, I mean. In the refraction, the deflection of light as it enters or passes through the atmosphere. So refraction is equals to 0.96 divided by tan multiplied by altitude. For altitude above 15 degrees, a simplified formula is adequate. It is plus minus 0 minutes 0.02. So it is also included in the almanac. So true altitude is the resultant altitude after all corrections are applied. So here the summary of altitude correction table for the star and planets in nautical almanac. And let's proceed to the example problems using the stars in getting the true altitude. So, first example is we're going to use the star Deneb. So the problem is the sextant altitude is 15 degrees, 22.6 minutes of star Deneb was taken on 26th of October, year 2018, with the index error 1.1 minute of the arc and the height of eye 15.5 meters. So find the true altitude of Deneb. So first, we're going to identify the givens. So sextant altitude is 15 degrees and 32.6 minutes, and the index error is 1.1 minutes of the arc, and the height of eye is 15.5 meters. Let's proceed. So the sextant altitude is 15 degrees and 22.6 minutes, and index error is 1.1 minutes of the arc. So this is the rule. Add if of the arc and subtract if on the arc. So the index error is of the arc. So we're going to add the sextant altitude to the index error. So the observed altitude is 15 degrees and 22.7 minutes. And the difference between sextant altitude and the index error, or the total between the sextant altitude and the index error, in this case, this is the total because it is of the arc. And the dip is 15.5 meters. So we're going to go to the nautical almanac altitude correction tables for 10 degrees to 90 degrees. So sun, stars, planets, and go to the deep area and find 15.5 meters. In finding the deep, always choose the correction above the height of the eye. So next, I'm going to go to the nautical almanac. So you can see here the encircle with the red pen. So this is the deep. So let's proceed. Since the height of eye is 15.5 meters, simply find the corresponding deep correction, which is above or inclined with the value of the height of eye, which is 6.9. So we can see here with the highlighted red highlighter, so the value is 15.5. So we're going to look above or inlined. So the value is 6.9. Next. In finding the deep, always choose the correction above the height of eye. So in the almanac, 15.5 meters is in between 6.9 minutes and 7 minutes, since 6.9 is above the height of eye. We chose 6.9 as the deep correction. Deep correction is always subtraction. So here's the how it's calculated. Sextant altitude 15 degrees 32.6 minutes, and add by the index error 1.1 minutes of the arc. Then the observed altitude is 15 degrees 23.7 minutes. Then the deep is to be subtracted by the deep, which is 6.9 minutes, and the result is our apparent altitude, which is 15 degrees 16.8 minutes. And the next step is to get the refraction correction. I'm going to proceed to the next page. So since the apparent altitude of a star, then if 15 degrees 16.8 is not in the refraction correction, we're going to use the correction that is in between 15.03 and 15.29, which is 3.5. So it is visible here with a red highlighter. We can see it highlighted by red. So in between is 3.5. Then, so apparent altitude is 15 degrees 16.8 minutes. Then the total correction or refraction is 3.5 minutes. Then we're going to subtract the apparent altitude to the refraction there. So the true altitude is 15 degrees 13.3 minutes. So the true altitude of star Denid is 15 degrees and 13.3 minutes. So the example number 2 is going to be discussed by next group mate, Lim Adrian Gabriel. That's all, sir. Thank you.
I'm Cadet Lim Adrian Gabriel, and I'm ready to continue Cadet Monte Calculus report on how to calculate the star. So here in example number 2 of star NF, sextant altitude is 31 degrees and 22.0 minutes. The star NF was taken on September 10, 2018. So its index error is 2.0, and the arc or the height of I is 3.0 meters. So we need to find true altitude of NF. So here are the given. First is the sextant altitude, which is 31 degrees and 22 minutes, and its index error is 2.0 on the arc, and the height of I is 3.0 meters. So to solve for observed altitude, subtract our sextant altitude by the index error, and which is 31 degrees and 22 minutes, subtracted by 2 minutes on the arc. So equivalent of, or we have our observed altitude, which is 31 degrees and 20 minutes. So the IP is 3.0 meters. So we, sub- we subtract our DIP we subtract our observed altitude by DIP, which is 3.0, and and there we can get our apparent altitude, which we have here is 31 degrees and 17 minutes. Next is the apparent altitude is 31 degrees and 17 minutes. So the total correction or refraction is subtracted by 1.6 minutes, which we consider the closest to 31 degrees and 17 minutes is between 30:22 and 31:58, which is 1.6. That's where we got our total correction or refraction. So to get our true altitude, we subtract our apparent altitude and total correction. So this is the result, and we got our true altitude, which is 31 degrees and 15.4 minutes. So the true altitude of star NF is 31 degrees and 15.4 minutes.
In continuation of our topic regarding to the calculations for the sextant altitude of stars and planets, I'm going to tackle now how to convert the sextant altitude of a planet into its true altitude. So converting sextant altitude to its true altitude of a planet is pretty much the same procedure as to the stars. Although there are some cases that additional corrections are needed, especially to celestial bodies that are near to the Earth, such as Venus and Mars. So in our example, which is finding the true altitude of planet Saturn, take note that the nautical almanac used in this discussion is not the official nautical almanac used on board, but rather a nautical almanac for practice only. So example 3 is the sextant altitude of 84 degrees and 32 minutes of planet Saturn was taken on June 8, 2018, with an index error of 5.5 off the arc and the height of I, which is 6 meters. So find the true altitude of planet Saturn. So the given are the sextant altitude of 64 degrees and 32 minutes, index error of 5.5 off the arc, and the height of I of 6 meters. Now that we know the given data, we're now going to organize it in the standard format, the same on the presentation. So next step is to find the observed altitude of the celestial body, which is Saturn, its dip, and its apparent altitude. So to get the observed altitude, simply find the algebraic sum of the sextant altitude and the index error. Take note that if the index error is off the arc, then we do addition, and subtraction if it's on the arc. So our example is sextant altitude of 84 degrees and 32 minutes, index error of 5.5 off the arc. So we're going to do addition since it's off the arc. So our sextant altitude of 84 degrees and 32 minutes plus 5.5 minutes of index error equals 84 degrees and 37.5 observed altitude. Next is we're going to find our dip. So we have a height of I of 6 meters. First, simply go to the nautical almanac under altitude correction tables for 10 degrees to 90 degrees for sun, stars, and planets, and go to the dip area. Simply locate our height of I and find what correction it is in line to. So our height of I is 6 meters, so it is in line to the dip correction of 4.3 minutes. So next step is to find the apparent altitude. So apparent altitude is the difference between observed altitude and the dip. So take note that the dip is always subtracted to the observed altitude. So our observed altitude is 84 degrees and 37.5 minutes subtracted to our dip, which is 4.3 minutes. So our apparent altitude is 84 degrees and 33.2 minutes. Now that we have our apparent altitude, we're now going to apply our total correction or the refraction correction. So same as with finding the dip, go to the Nautical Almanac altitude correction table for 10 degrees to 90 degrees for sun, stars, and planets. Then find the corresponding refraction correction that is in line to our apparent altitude. So our apparent altitude is 84 degrees 33.2 minutes. So find the refraction that is in line to it. So 84 degrees 33.2 minutes is in line to 0.1. So our total correction is 0.1. Next step is to find the true altitude, which is the difference between apparent altitude and the total correction. So our apparent altitude 84 degrees and 33.2 minutes subtracted to 0.1. The true altitude of planet Saturn is 84 degrees and 33.1. Next example is finding the true altitude of planet Jupiter. So example 4, the sextant altitude of planet Jupiter is 75 degrees and 17.0 minutes. It was taken on November 1, 2018 with an index error of 4.7 on the arc and the height of eye of 8 meters. So the given are the sextant altitude of 75 degrees and 17 minutes, index error of 4.7 on the arc, and the height of eye of 8 minutes. Now that we know the given data, we're now going to organize it in the standard format, the same on the presentation. Next step is to find the observed altitude of the celestial body, its dip, and its apparent altitude. So remember that the observed altitude is the algebraic sum of the sextant altitude and the index error. So our sextant altitude is 75 degrees and 17.0 minutes, and our index error is 4.7 on the arc. So we're going to use subtraction here. So 75 degrees 17 minutes minus 4.7 is 75 degrees and 12.3 minutes. So our observed altitude is 75 degrees and 12.3 minutes. Next step is to find the dip. So we have a height of eye of 8 meters. Simply go to the Nautical Almanac under the altitude correction tables for 10 degrees to 90 degrees for sun, stars, and planets, and go to the dip area. So simply locate the dip correction that is in line to our height of eye of 8 meters. So our height of eye of 8 meters is in line to the dip of 5.0. So since we have our dip, next step is to find our apparent altitude, which is the difference between the observed altitude and the dip. So our observed altitude of 75 degrees and 12.3 minutes subtracted to 5.0 dip is equal to 75 degrees and 7.3 minutes. So our apparent altitude is 75 degrees and 7.3 minutes. Now that we have our apparent altitude, we're now going to apply our total correction or the refraction correction. So same as with finding the dip, go to the Nautical Almanac altitude correction table for 10 degrees to 90 degrees for sun, stars, and planets. Then find the corresponding refraction correction that is in line to our apparent altitude. So our apparent altitude is 75 degrees and 7.3 minutes. So it is in line to 0.3 total correction. So to find our true altitude, simply subtract the apparent altitude to the total correction. So our apparent altitude of 75 degrees and 7.3 minutes subtracted to 0.3 total correction, our true altitude is 75 degrees and 7.0 minutes. So the true altitude of planet Jupiter is 75 degrees and 7.0 minutes. That's all for the sextant altitude calculation for planets.